December 19th was not just another date on an astronomical calendar. It marked the closest approach of 3I Atlas to Earth during its entire journey through the solar system. For scientists, this was the single best observational window humanity would ever have. There would be no second pass, no return visit, and no opportunity to correct missed measurements later. Everything depended on what could be captured within this narrow slice of time. Across the world, ground-based telescopes were ready. Observatories coordinated their schedules and instruments were carefully calibrated. Expectations quietly built, not only among scientists, but also among the public following the story. Many assumed that this moment would bring sharper images, clearer data, and perhaps a definitive update from NASA itself. After all, this was the moment everyone had been waiting for. And yet, when the moment passed, something unexpected happened. There was no urgent press conference, no dramatic announcement, no single image that suddenly explained everything. Instead, what followed was a restrained and deliberate quiet. Updates were minimal. Statements were cautious. For many observers, this silence felt strange, almost uncomfortable, especially after so much anticipation. That quiet quickly led to a familiar question. Did NASA see something unusual during the flyby and choose not to say it yet? Or was this simply how science behaves when data is still being processed and understood? In moments like this, silence does not feel empty. It feels charged with meaning, inviting curiosity rather than offering closure. If this truly was the golden moment of observation, why did it pass without a major declaration? And what does that silence suggest about what NASA may already know, but is not yet ready to say out loud? During the Earth flyby, NASA did not walk away empty-handed. From a scientific standpoint, this was one of the most data-rich moments of the entire encounter. Precise orbital measurements were refined as 3I Atlas passed through a geometry that allowed tracking with exceptional accuracy. Subtle changes in brightness were recorded over time, offering clues about rotation, surface behavior, and possible activity. At the same time, spectral signals were captured across multiple wavelength bands, each one carrying fragments of information about composition and physical processes. But nearly all of what NASA collected during those hours existed in its raw form. These were not conclusions or polished discoveries. They were streams of numbers, light curves, and spectral traces still mixed with noise, instrumental artifacts, and observational limitations. On their own, raw measurements rarely carry clear meaning. Isolated data points can be especially misleading when the object moves fast and behaves unlike anything commonly observed in the solar system. For that data to become useful, it must pass through a careful and time-consuming process. Noise has to be filtered out, instrumental biases corrected, and results tested against physical models that were never designed with interstellar visitors in mind. Most importantly, every signal needs to be compared with independent observations from other telescopes and other teams. Only after this process does data begin to turn into knowledge. This is where the quiet gap between NASA and the public begins to form. NASA knows more simply because it holds the raw data in full resolution, in full context, and with all of its imperfections intact. The public, by contrast, only ever sees what survives this entire filtering process. Knowing more does not mean understanding everything yet, and it certainly does not mean being ready to speak with confidence. Raw data can be powerful, but it can also be deceptive. Released too early, it can suggest patterns that disappear under scrutiny or hint at conclusions that later fall apart. Raw data has a tendency to tell convincing stories before the full picture is clear. In what ways can raw data mislead us if it is released before it has truly been understood? In astronomy, raw data is rarely a single clear signal pointing in one obvious direction. More often, it is a collection of measurements that partially agree, occasionally contradict each other, and constantly compete for interpretation. Atmospheric interference can distort incoming light. Viewing angles can exaggerate or hide certain features. Instruments themselves introduce subtle biases that only become visible after careful calibration. What looks meaningful at first glance may simply be an artifact of how, when, or from where the observation was made. This is why an unusual signal observed today does not automatically survive tomorrow. A spike in brightness can vanish once background noise is removed. A strange spectral feature can disappear after correcting for instrumental effects. In many cases, the most intriguing anomalies are the first things to fade when the data is properly cleaned. Releasing such signals too early risks turning temporary illusions into permanent misconceptions. NASA avoids publishing data that has not yet passed cross-checks for this exact reason. Different instruments must agree. Independent teams must reach compatible results. Models must be tested and retested. This is not about secrecy or control. It is about protecting the integrity of scientific knowledge from being shaped by incomplete or unstable evidence. From the outside, however, the public only sees the end result. The uncertainty, the false starts, and the discarded interpretations remain invisible. That unseen process creates a gap in perception. When conclusions arrive without the long path that produced them, it can feel as if something was withheld. The impression that they know more than they are saying grows naturally in that space. But if everyone were given access to every piece of raw data from the beginning, would understanding actually improve? Or would the noise drown out the signal and lead us further from the truth than before? 3I Atlas is not just another small body passing through the solar system. It is an interstellar object, formed somewhere beyond our stellar neighborhood and only briefly visiting before continuing on its path into deep space. That single fact changes everything about how it must be studied. Unlike comets or asteroids bound to the Sun, this object offers no long-term relationship, no future return, and no second opportunity to observe it under better conditions. There is no dedicated mission that can be launched to chase it. No spacecraft can be redirected for a closer look. Every observation must be done remotely, from a distance, and within a limited window that cannot be extended. Once it leaves, it is gone for good. Any mistake made in interpretation cannot be corrected later by simply waiting for another pass. This reality forces NASA into a much higher level of caution than usual. With typical solar system objects, uncertainty can be reduced over time. With 3I Atlas, uncertainty compounds. Some of its observed behaviors do not align cleanly with what scientists expect from familiar comets. Subtle inconsistencies appear in how it reflects light, how its brightness changes, and how its activity responds to solar influence. None of these differences are dramatic on their own, but together they resist easy classification. As uncertainty increases, so does the cost of being wrong. A premature conclusion about an interstellar object would not just be embarrassing, it could shape scientific models incorrectly for years to come. In cases like this, slowing down communication becomes a form of responsibility rather than hesitation. If an object will never return and every conclusion must stand forever, what are the consequences if NASA gets it wrong the first time? In science, knowledge does not move in a straight line from observation to announcement. It passes through distinct layers, each with its own rules and responsibilities. First comes what researchers actually see in the data. Then comes the more tentative space of interpretation, where patterns are explored and possible meanings are debated. Only after that does science reach the stage of what can be said responsibly in public, with confidence that the message will not mislead. NASA almost always speaks from this final layer. Its public statements are shaped by what can withstand scrutiny, replication, and long-term examination. But the public is rarely interested in that stage alone. Curiosity naturally gravitates toward the middle layer, where ideas are forming. Uncertainties remain open, and the story feels alive. That is where imagination fills the gaps. And where speculation feels most compelling, the distance between these layers creates tension. When NASA limits its communication to carefully verified conclusions, it can appear as if something is being held back. In reality, there is often a rich internal landscape of hypotheses and competing explanations that simply have not earned the right to be spoken out loud yet. Saying them too early does not increase understanding. It risks freezing uncertainty into misleading headlines that are difficult to undo. This is why restraint becomes part of scientific responsibility. Choosing accuracy over immediacy is not an attempt to control the narrative. It is an attempt to prevent fragile ideas from being mistaken for established facts. When knowledge exists in stages and the most interesting ideas live in the middle, should science prioritize complete transparency? Or should it protect accuracy, even if that means speaking less? One of the most common questions after the flyby was simple and direct. Why were there no stunning, close-up images after December 19th? For many observers, the absence of dramatic visuals felt like a missing payoff, especially after weeks of anticipation. The answer is less mysterious than it appears. Even at its closest approach, 3I Atlas was still extremely far away by astronomical standards. It was moving rapidly across the sky, giving telescopes only brief moments to collect light. On top of that, its intrinsic brightness was low, limiting the amount of detail that could be resolved. These constraints make producing sharp, cinematic images extraordinarily difficult, no matter how advanced the instruments are. More importantly, striking images are not always the most valuable form of data. In cases like this, spectroscopy and precise brightness measurements carry far more scientific weight. They reveal how the object interacts with sunlight, how its activity evolves, and what physical processes may be at work. The problem is that these kinds of data are abstract. They do not translate easily into visuals that excite a general audience or fit neatly into a headline. Faced with that reality, NASA often chooses restraint. Releasing an image that looks impressive but carries the wrong implication can do more harm than saying nothing at all. A beautiful picture can suggest proximity, certainty, or detail that simply is not there. Silence, in this case, becomes a way to avoid misleading the public rather than a sign that something is being hidden. So when the images never arrived, was NASA failing to deliver spectacle? Or were we expecting the universe to perform for our curiosity rather than reveal itself on its own terms? Once the flyby was over, the most visible part of the event ended. But the most important work began. The data collected during those critical hours did not move directly toward publication or public explanation. Instead, it entered an internal review phase that unfolds almost entirely out of sight. Different teams began cross-checking one another's results, looking for consistency, contradictions, and subtle signals that only appear when datasets are compared side by side. At the same time, observations were tested against existing models that were never designed with interstellar objects in mind. Assumptions had to be questioned. Weak hypotheses were gradually eliminated as evidence failed to support them. This process is slow by necessity. It can stretch across weeks or even months, especially when the object being studied does not fit neatly into known categories. This phase does not align with the rhythm of news cycles or social media updates. There are no clean milestones to announce and no conclusions stable enough to summarize. Yet, this is precisely the stage where science is most active. Decisions made here determine whether a result will endure or quietly collapse under further scrutiny. During this period, NASA often knows more than it appears to. Patterns begin to emerge. Certain explanations lose credibility while others gain weight. But none of this is ready to leave the internal space where uncertainty is still being resolved. Speaking too soon would freeze a moving process into a fixed narrative. If the most intense scientific work happens when nothing seems to be happening at all, could silence itself be the clearest sign that discovery is truly underway? With an object like 3I Atlas, speculation is almost irresistible. Every unusual measurement invites a new idea. Every deviation from expectations opens the door to multiple explanations. In the early stages, many of these hypotheses can feel equally plausible, especially when data is limited and the object itself refuses to behave like anything familiar. From the outside, it may seem as though science is standing on the edge of exciting possibilities. But speculation has a fragile life once it leaves the scientific context. Ideas that are meant to be provisional can quickly harden into apparent conclusions. Nuance is lost. Conditions and caveats disappear. What begins as a cautious suggestion can be transformed into a definitive claim by the time it reaches headlines or social media. Speculation is not dangerous inside a research group, but it becomes volatile when released into a global information ecosystem that rewards certainty and speed. NASA has learned this lesson the hard way. In the past, premature statements have led to public confusion, damaged credibility, and long-lasting misconceptions that were nearly impossible to correct. Those experiences shaped a culture of restraint. Today, NASA tends to err on the side of silence rather than risk allowing an unfinished idea to escape into the public narrative. The tension arises because the public often wants the opposite. Ambiguity fuels curiosity. The less clear the picture, the more people lean in, searching for meaning. When NASA refuses to speculate, that curiosity does not disappear. It collides with institutional caution, and the gap between them becomes a source of frustration. When a hypothesis is still forming and the world is eager for answers, who ultimately bears responsibility if an unripe idea is misunderstood on a global scale? NASA is not lying. It never was. What it does instead is far less dramatic, but far more important. NASA chooses not to speak when certainty has not yet been earned. In a world trained to expect instant explanations, that choice can feel unsettling. But it is also the reason scientific knowledge holds its shape long after headlines fade. Saying that NASA knows more than it is saying does not imply a hidden agenda. It reflects the reality of how science functions behind the scenes. Knowledge arrives in layers, and only the most stable ones are released into public view. Everything else remains in motion, tested quietly until it can stand on its own. 3I Atlas has already passed through our solar system, carrying with it a fragment of a story that began far beyond our sun. We will never see it again, but the questions it left behind did not leave with it. They now live in datasets, in models still being refined, and in debates that will shape how future interstellar visitors are understood. In that sense, the silence surrounding 3I Atlas is not an ending. It is a transition. It marks the moment when curiosity gives way to patience. And when spectacle gives way to understanding, how we respond to that silence will influence not only what we learn next, but how we choose to learn it. If science needs time to speak the truth carefully, are we prepared to listen when it finally does? Modern news operates under clear constraints. Headlines must be short. Messages must be instantly understandable. Stories are expected to deliver clarity quickly, often within a few sentences. This structure works well for events with clear outcomes, but it clashes with the nature of scientific discovery, which is rarely clean or final. Science is conditional by design. Results come with uncertainties, assumptions, and margins of error. Explanations depend on context and often change as new data is added. When these layers are compressed into a headline, much of the meaning is lost. What remains is a simplified version that feels complete, but is missing the subtle connections that actually matter. When NASA chooses to speak carefully or says very little, the challenge for journalists becomes even greater. With limited official language to work from, writers must fill gaps, summarize complexity, and keep readers engaged at the same time. Inevitably, details are trimmed away. Caveats disappear. What was meant to be provisional can sound definitive, and what was uncertain can appear resolved. From the audience's perspective, this creates a strange effect. The story feels incomplete, as if key pieces are missing. That sense of absence does not read as caution. It reads as omission. Suspicion grows not because of what is said, but because of what seems absent from the narrative. So when confusion takes hold, is the problem rooted in NASA's restraint, or in the way complex science is reshaped to fit the demands of modern news? Inside NASA, the picture is rarely empty. Even without final conclusions, scientists often develop preliminary models that begin to outline what an object might be like. In the case of 3I Atlas, there may already be early frameworks describing its possible structure, a range of likely compositions, and physical scenarios that best fit the observations collected so far. But these internal models are not answers. They are working tools. Each one carries assumptions that could change as data is refined or reinterpreted. Speaking about them publicly at this stage would invite them to be treated as conclusions rather than hypotheses. Once an idea reaches the public, it is difficult to pull back, even if later evidence weakens or overturns it. This is why NASA often keeps such insights confined to internal discussions. The goal is not secrecy, but patience. By waiting until evidence reaches a higher level of certainty, NASA protects the scientific record from becoming cluttered with claims that were never meant to stand on their own. This approach may feel unsatisfying to an audience eager for answers, but it is deeply normal within science. Knowledge is allowed to mature quietly before it is introduced to the world. The question is whether we are prepared to engage with science as it truly operates, or whether we only want conclusions that feel finished, even when the universe itself is still mid-sentence. Interstellar objects sit at the edge of what modern astronomy is prepared for. There are only a handful of confirmed examples, and each one behaves differently enough that comparisons offer limited guidance. Theoretical models exist, but they are broad and incomplete, built on assumptions rather than rich observational history. When something like 3I Atlas appears, scientists are not just analyzing a new object. They are testing the boundaries of their own frameworks. Every new data point has disproportionate weight. A small discrepancy can challenge an entire model. A subtle trend can force researchers to reconsider ideas that seemed stable just days earlier. Under these conditions, conclusions cannot be rushed. What works for familiar comets, observed over many orbits and decades, does not apply cleanly to an object that arrives once and then disappears forever. As uncertainty grows, caution multiplies. Each statement carries more risk. Because there is less precedent to anchor it, silence becomes a buffer, a way to keep fragile ideas from solidifying too early. With interstellar objects, the absence of quick explanations is not hesitation. It is an acknowledgement of how little margin for error exists. When faced with something entirely new, should science move quickly to satisfy curiosity, or slow down to protect understanding from its own assumptions? The modern public is used to immediacy, live streams, real-time updates, and constant notifications have reshaped how information is consumed. When something important happens, people expect to watch it unfold moment by moment, with explanations arriving almost as quickly as the event itself. Science does not operate on that schedule. Data must be collected, checked, debated, and rechecked before it becomes meaningful. There are pauses where nothing visible happens. Even though intense work is underway behind the scenes, this mismatch between expectation and reality creates a growing gap, one that 3i Atlas exposed with unusual clarity. NASA did not suddenly slow down after the flyby. Its pace remained consistent with how science has always worked. What changed was the level of public attention and the demand for constant engagement. As expectations rose, the absence of frequent updates began to feel like withholding rather than process. This gap leaves an uncomfortable question hanging in the air. When we press for faster answers and louder explanations, are we asking science to do its job better? Or are we asking it to perform in ways it was never meant to? In science, silence is often misunderstood. From the outside, it can look like hesitation or avoidance. But within the scientific process, it usually signals something else entirely. Silence is a form of quality control. It creates space for verification, correction, and reflection before ideas are exposed to public scrutiny. By slowing communication, scientists reduce the risk of locking in conclusions that may later prove fragile or wrong. This restraint protects more than individual results. It protects credibility itself. Scientific trust is built not on speed, but on reliability over time. Each statement that survives careful review strengthens that foundation. Speaking too often or too confidently in moments of uncertainty can erode it just as quickly. At the same time, silence carries a cost. When information is withheld, even for responsible reasons, a vacuum forms. That empty space rarely stays empty for long. Speculation, interpretation, and narrative filling rush in to occupy it. Some of this is thoughtful curiosity. Some of it is guesswork. Some of it turns into assumptions that feel real simply because no alternative explanation is visible. This tension is unavoidable. Silence safeguards knowledge, but it also invites misunderstanding. Navigating that balance is one of the hardest challenges modern science faces, especially when public attention is intense. Is it possible for science to remain cautious and precise without losing the trust and engagement of the people watching from the outside after the flyby? The story of 3i Atlas did not end. It simply moved into a quieter phase. The data collected continues to be examined, refined, and reanalyzed as new techniques and comparisons are applied. This work unfolds slowly, not because of secrecy, but because careful science cannot be rushed without consequences. The results of this process are unlikely to arrive in a single announcement. Instead, they will emerge gradually through research papers, conference discussions, and technical publications. Each release will add a small piece to the larger picture, often without the dramatic framing that public audiences have come to expect. progress will be incremental rather than cinematic. For those following the story, this can feel unsatisfying. There will be no definitive moment when everything suddenly makes sense. Understanding will grow in fragments, with some questions answered and others left open. This is not a failure of communication. It is the normal rhythm of scientific advancement. As the data continues to speak in its own careful language, the real question becomes one of patience. Are we willing to wait for knowledge to take shape through evidence? Or do we only listen when science speaks in headlines?